or do anything. Okay, so any questions again? Anything? Anything? Okay, we'll continue with 2.5. The title is Transformations. However, we can't talk about transformations before we list the most important functions and their simplest possible form. So, linear. Can anyone give us the easiest possible, simplest possible linear function that you can think of? Say it again. You mean just x because it's linear. Yes, we're going to get to quadratic in a minute. So we're going to graph this, and we get this graph. So this is y equals x. Is this function symmetric by any chance? Odd, even, or none of the above? It is odd, symmetric with respect to the origin. Very good. It is. The function is odd. Now quadratic. The simplest possible quadratic function, already Blue told us, it's x squared. So here's the graph of x squared. Is this function odd, even, or none of the above? Yes, symmetric with respect to the y-axis, so this function is even. Perfect. Let's say cubic. Can anyone give us the simplest possible cubic function? That's it. Excellent. We used it before. When you see the graph, you'll say, oh, yeah, I've seen this before. And here it is. Y equals x cubed. Is this function odd, even? Yes, very good. The function is odd, symmetric with respect to the origin. Stop me anytime if you have questions, please. Anytime. Okay. What about the square root? The simplest possible square root? That's it. The square root of x. Here's the graph of the square root of x. Do not graph it as a straight line. It's not a straight line. Is this function odd, even, or none of the above? Of course, it's not symmetric. Okay, so let's look at the cube root. Can anyone give us the simplest possible cube root? Yes, of course. This is the cube root of x. Odd, even, or none of the above? Very good. Indeed, it's an odd function. And the last one we would like to mention is the absolute value. The simplest absolute value, absolute value of x. And it looks like a v. Odd, even, or none of the above? Symmetric with respect to the y-axis, very good, it's even. Okay, so yes, I listed 7 functions. So what? 7 or 8? Or was it 8? 6. 6, very good. I listed 6 functions. So what's the big deal with this? Here it is. And because we are going to look at this problem towards the end of the class today, I would like to take a look at this graph. So at 10 months old, the median height for boys is this, whatever that is. At 20, yes, perfect. At 20, at 30, and so on and so forth. So what they did, they selected a certain number of boys that are 10 months old, other number of boys, certain number, it could be 10,000. I don't know how they created the study or what was the protocol. But anyway, so they got this point for 0 months, they got this point for 10 months, they got this point for 20, and so on and so forth. And then they graphed this function, and then they said, well, let's think about it. Is there a model, is there a function that we could fit and that goes pretty close? It will not hit each and every point, but it will go very close or through most of the points. And they said, okay, well, let's see what functions we know. There are way more functions than just these, and you will see we are going to add 2 more functions to the list. Actually, 3 more functions to the list this semester. Will this fit? No. Will this fit that model? No. Will this fit that model? No. Will this fit the model? No. Will this fit the model? No. Yes, because it's a positive x value. It's not negative. It cannot be negative. So I cannot use the cube root because the cube root can be taken from positive and also from negative values. But the positive is the square root. Of course, there are some transformations on this function. As you saw it, it's somewhere here. It's not here. So they have done something to it. And when we say something has been done, we are talking about transformations. And we have 3 categories. We can't look into transformations without knowing these 6 functions. There is more, the rational function and a few others, but 6 is enough for now. So we know we need to remember their shape or their graph, and then you will see without even graphing a function, we will be able to picture the graph in our mind, and we can talk about it without even graphing it, and you'll see how this works. Okay, so let's start by listing the transformations. As I said, there are 3 categories and 2 categories within each category. Shifts, reflections, stretching, shrinking. So 3 categories and 2 categories, subcategories in each. So shifts, reflections, stretching, or shrinking. That's okay. Okay, so let's start with the shifts. Thank you. There are 2 categories, horizontal and vertical. We'll come back to the rest and we'll fill in the rest of the table in a minute. Okay. So let's suppose I am asking you to tell me what I'm doing or what is happening here with this function. I'm going to create a function. Here it is. I'm going to create another one, completely independent of each other. And let's start with the first one. I'm going to ask you which of these 6 functions that we listed a few minutes ago I used to create this function. Very good. So we used x squared. Now, I did something to this. I did something to this function to create this one. And there are only 2 possibilities. Did I change x or did I change y? Any change in x does this to the graph. Any change in y does this to the graph. Okay? So let's take a look. Compare. Here I have just x, but here I have x plus 3. The positive 3 touches x. So it's a transformation on x or on y? Right, because I'm changing x into x plus 3. When I graph this function, what I like to call the base function or the simple function, here's the graph of x squared. And the x-intercept is at 0. Would you agree? Okay, now I would like to identify what this transformation do to x squared. Where will the x-intercept be for this function? But if I put 3 plus 3 is 6, and 6 squared is 36. Is 3 comma 36 an x-intercept? So 3 is not the one. It shifts to the left, so at x equals negative 3. So this is x plus 3 squared, and it shifts right on top of negative 3. So this first function is a horizontal shift 3 to the left. 3 units, of course. Horizontal shift 3 units to the left. Okay, so now forget about f. Let's analyze what does x minus 2 do to x squared. Am I changing x or am I changing y? I'm changing x. Again, x squared has the x-intercept at 0. Where does x minus 2 have the x-intercept? Do we all agree with 2? 2 minus 2 is 0? Okay, so this is a horizontal shift of 2 to the right. So this is x minus 2 squared over 2. So function g, horizontal shift of 2 units to the right. I don't want you to memorize. Students sometimes ask, oh, good, so if it's x minus 2, it's to the right, and if it's x plus 3, so yeah, that's fine. But what you should remember is I'm looking for the x-intercept when I shift left and right. Right? It has to stay on the same horizontal, on the same y equals 0. That's the x-intercept, y equals 0. So if it was here at 0, then x minus 2 has to go to 2. And if it's here at 0, then x plus 3 has to go to negative 3 to stay horizontally. If I put in one more time here, 3 plus 3 is 6. 6 squared is 36. But 3 comma 36 is not on the x-axis. It does not have y equals 0. Okay, so this was a horizontal shift. Okay, I'm going to create another function now. Let's say f of x equals the absolute value of x minus 3, and g of x independent of f, the absolute value of x plus 1. Which function did I use now from our list of 6 to create f and g? Of course, I used a different function, which is the absolute value, so y equals the absolute value of x. I know how to graph it. It's that v-looking type of function. So this is the y, the absolute value of x. And now I'm analyzing like before, because I have to understand what type of transformation this is. Is it a transformation on x, or is it a transformation on y? So let's compare. Am I changing x? Is there something that inside the absolute value changes this x into something else? No. So then the x values are the same. This one is a value plus 0, and this one is a value, the same value, but minus 3. Same thing here. This one is a value plus 0, but this is a same value, but plus 1. What do you think will happen? And since it's not a transformation on x, it must be a transformation on y. So as we said, when we change y, we're going up and down. So then how will you graph this function by comparison or in comparison to the absolute value of x? Down 3. Very good. 1, 2, 3. So this is the absolute value of x minus 3. Very good. And then how will you graph, or where will you graph the absolute value of x plus 1? Yes, so up 1. So this is the absolute value of x plus 1. So this was the second in line. So this is a vertical transformation. Good. So let's move on. I would like now to create a combination, a combo of both transformations. So let's say f of x equals the cube root of x plus 1 minus 3. Which function did I use now? I used y equals the cube root of x. Perfect. I'm going to graph the cube root of x. Here's the graph. Notice that this is not a straight line. Do not graph it as a straight line. So this is the cube root of x. Now, obviously, I see two transformations here. The first transformation, it has all of it, everything has to be in order of operations. So now I can say, wait a minute. What order of operations? What are you doing? You're not evaluating. As if I were to evaluate. So for example, if I ask you to evaluate this function for x equals 7, which operation would you perform first? Correct. The 7 plus 1 first, right? Then you're done with the cube root, and then you subtract 3. Very good. So the first transformation would be the cube root of x plus 1. What does this mean? What does this do to the cube root of x? Yes. Left shift of 1 unit. Now, function number 2 is a transformation on function 1, not on that anymore. That's gone. Number 2 is a transformation on number 1, which will be the cube root of x plus 1 minus 3. Again, I compare. Nothing changes here. This is plus 0, but this is minus 3. And no x is changed in any way from 1 to 2. So then, what do? What transformation is 2 on function number 1? Very good. Exactly. Down 3 units. I have to graph that one more time. Forgive me, because I did not have enough room there. So I'm graphing the cube root. Then you told me to shift left 1. Fine. I'm going to shift left 1. It should have been a little bit flatter. Okay. So this is the cube root of x plus 1 at negative 1. And then you told me to shift this 3 units down. Okay, no problem. So this is the graph of the cube root of x plus 1 minus 3. So when I have several transformations, I like to do this just to signify that that is the final graph. So there is no confusion there, and you see it clearly. Is this okay? So far, so good? Okay. Moving on then. Let's look at the following graph. F of x equals the square root of negative x. And g of x, independent of that, negative the square root of x. Now, please tell me which function did I use. I should denote that by y. I want to denote it by y, not to be confused with this. So which function I used to create function f and function g? Very good, of course. I used the square root of x. Good. And now let's analyze what is happening here. Let's compare the first two. This is x, and there is a negative that touches x. It's not outside, like here. It touches x. Here it does not touch x. It's x, and then the square root of x, and then minus 1. Here, it's x multiplied by negative 1. So let's compare and decide if I'm changing x or changing y. Say that again. So my question is, from x to negative x, is that a change in x or a change in y?
Yes.
Of course. So here's what we're trying to do now. From x to negative x, or from x to negative x. What am I doing to the graph this time?
Well, the graph is increasing.
It doesn't increase or decrease.
Positive is the positive factor next to graph is increasing. And so, negative x.
By replacing x by negative x, I reflect the graph with respect to the y-axis. Okay, that's it. Awesome, yes. So here's the graph of the square root of x. And here will be the graph of the square root of negative x, which is a reflection with respect to the y-axis. This reflection with respect to the y-axis. That's all it does. By changing 2 into negative 2, I'm reflecting the graph with respect to the y-axis. By changing negative 5 into the opposite of negative 5, which means 5, I'm reflecting the graph with respect to the y-axis. That was done. Now let's analyze these two. Am I changing x here? No. So this one has positive in front of the y value, and this one has negative in front of the y value. What am I doing now? Exactly. That's what it is. So here is the graph of negative the square root of x. So this transformation is a transformation on y, is a reflection with respect to the x-axis. Any questions so far? So we check the reflections now with respect to the y-axis and with respect to the x-axis. Check, check. And now let's use a combo, a function that has all these and the above. Ready? So here's a combo. F of x equals negative x plus 2 in absolute value plus 3. Again, in order of operations, I have to present all transformations here. Number one, I have to identify the function that was used. The absolute value of x is the function that was used here. Very good. First transformation in order of operations. Yes, you're going to say x plus 2, which is a horizontal shift. Which direction? Very good. Left 2. Number 2 is negative the absolute value of x plus 2. No, it has to be in order of operations. You have to multiply first by negative 1, and at the end you add 3. So if I'm asked to evaluate this for 4, I will do 4 plus 2, not plus 3, but first multiply by negative 1 and then plus 3. No. from left to right, but if it's addition or subtraction, but if it's multiplication, it's not from left to right. You have to perform the multiplication first.
If x plus 2 was in parentheses, not absolute value, wouldn't that, is that the only way you would shrink? You would shrink it when it's an absolute value?
The stretching and shrinking requires a number in front of y that is either greater than 1 or less than 1. Yes, you're way ahead of me, which is great, but we haven't gotten to that yet. In a minute.
I didn't know.
Yes, in a minute. Yes, we will definitely talk about that in a minute. Yes, Larson, go ahead. Is that okay? You had something to say?
Well, I was,
Go ahead.
I didn't even knew that.
So yes, so on the order of operations first, we deal with parentheses, assuming we don't have any grouping symbols, let's say. Then you have the first priority is power. The second priority, multiplication and division, as you said, from left to right. And then addition and subtraction, and then the order doesn't matter. Even if they say from left to right, it doesn't matter, trust me. But that's why we have multiplication here. We have to multiply first by -1. So when I complete this operation, then I multiply by -1, and then at the very end, I add 3. Does that answer your question? Okay, perfect. So what happened from here? Because this is not a transformation on that. Oh, no. This is a transformation on number 1. So compare these two and say, I know you are changing this, and that's why the function does that. What am I changing from here? Yes, but am I changing x or am I changing y? That's very important to know. It does not, x does not touch, -1 does not touch x. So as you see, there is no change between this and this. The change is the positive outside changes into a negative outside. So it does not touch x. It cannot be a transformation on x. It's completely outside. Yes, so this is a reflection with respect to, if it's a transformation on y, it cannot be with respect to the y-axis, but with respect to the x-axis. Very good. Is that clear? Don't let me move on if something is not clear, please. And number 3 is this, which is a transformation on number 2. Compare and see if x changes, or this value has 3 added to it. So what type of transformation? Is it on x or on y? So exactly, the positive 3 does not touch x. If from one step to the other, the transformation touches x, it's a transformation on x. Bless you. If from one step to the other, it increases or decreases, it cannot touch x. It will be a transformation on y. So it's a shift up 3. Ready to graph this? Very good. So here is the base function that I like to call. I call it base function, or basic function, the function that was used here. Then you told me to shift it to the left 2. Fine, I'm shifting it to the left 2. So this is x plus 2 in absolute value. Then you told me to reflect it with respect to the x-axis. I'm reflecting it. And then you told me to move it up 3. Very good. I'm moving it up 3. Again, when I have too many in there, I like to do this. So we know that this is the final graph. When graphing transformations, do you think that these graphs are exact? No, absolutely not. This is just a quick graph to understand what's happening with the function. That's all. Okay, Okay, I think we are ready for the last group. So let's take a look. Let's say we want to look at twice x squared, and then g of x, which is 1/2 x squared. Which function did we use now to create these two, f and g? Very good. Indeed, the base function is quadratic. Here's the graph of x squared. And now let's think about 2x squared. So this is the graph of x squared. Is this a transformation on x or on y? So first of all, compare. Is x squared the same with x squared? If they are the same, it cannot be a transformation on x. It's outside. So x squared is the same with x squared. If this is x squared and this is x minus 2, everything squared, then I'll say it's a transformation on x. But x squared and x squared have no change. So this one has 1 in front and this one has 2 in front. So if this is x squared, how would I graph twice x squared? So the height here is 1x squared. This height is 2x squared. It's a vertical stretching of the graph by a factor of 2. This is x squared. This is twice x squared. What about x squared to 1/2 x squared? What would that do? All heights get divided by 2 because it's a transformation on y. So this is x squared. This is twice x squared. This is x squared. This is 1/2 x squared. Yes? Okay. So here is twice x squared. And here is 1/2 x squared. The first one is a vertical stretching by a factor of 2. And this one is a vertical shrinking by a factor of 1/2. Okay, let's create another combo. Till we look before we look at the. I would like to look at the word problem that we with the boys, the height of boys, and then we'll go back to the last one. And then I hope we have a few minutes to look at some problems in the text in 2.5. Okay, here's a combo. A lot of transformations here. X plus 1 is a transformation, 2 is a transformation, -1 is a transformation, and -4 is another transformation. We have to start as if we are evaluating in order of operations. So first of all, I'm going to ask you which function did we use to create this one?
Y.
Very good. First transformation in order of operations. Which one? Yes, indeed, x plus 1 squared, left 1. Number 2 is a transformation on number 1. And unfortunately, I have to separate these two because this is one transformation and this is another. It doesn't matter if you do this first or this first, but I recommend do this first, this second. So this is 1, this is 2, this is 3, and this is 4.
So you multiply x plus 1 times 2.
Yes? What transformation is this? No, it's a number greater than 1.
Stretching.
Yes, vertical stretching. Number 3 is the transformation on number 2, and it's minus 2 x plus 1 squared. Is it a transformation on x or on y?
Why?
Of course, it doesn't. This number and this number do not touch x. If they don't touch x, they have to be outside. So it's a transformation of y. So what does this do to this graph? With respect to? Excellent. Reflect with respect to the x-axis. Finally, negative 2 x plus 1 squared minus 4. What does this do to this graph, the graph from number 3? You understand that this is not a transformation on that. This is a transformation on 3. 3 is on 2. 2 is on 1. So what do we have here?
Vertical shift down.
Excellent, because there is nothing else but the height changes, down 4. Excellent. Okay, I start with the base function, the simplest function used here, which is this. Then you told me to shift it left 1. Okay, fine, I'll shift it left 1 right here. Then you told me to stretch it by a factor of 2. Okay, I'm stretching it by a factor of 2. Twice x plus 1 squared. Then you told me to reflect it. Fine, I will reflect it. So this is negative 2 x plus 1 squared. Finally, you told me to move it up, down 4. Okay, I'm moving it up, down 4. And that's final. Can anyone give us the vertex of this function? The vertex, we're going to discuss it again in chapter 3. The vertex is that point, the max of the parabola or the quadratic function. Can anyone give us that vertex? The coordinates of this point? Awesome. Awesome. And we didn't calculate anything. We just graphed it using transformations, which is not a 100% graph, but it gives us at least that point. Very good. Let's look at the height of boys, and then we'll come back to the last transformation. Okay, so here's what the graph is all about. And in the first question, we are asked to classify this and first of all, at what type of function this is, and also look at the model that they created and explain how the model was determined. In other words, which transformations are involved. So, look at the model. 2.9 times the square root of x plus 20.1. Which function did they use to model the heights of boys between 0 and 60 months? The square root of x. Very good. What did they do to it first? First transformation on the square root of x. They stretched it by a factor of 2.9. Vertical stretching by a factor of 2.9. It's completely outside. It does not touch x. Good. And then what did they do to the graph? Shift it up 20.1. So it's stretched vertically by a factor of 2.9 and shifted up by 20.1. Excellent. So that was our first question, part A. Let's write it down. And then part B, they're asking us to determine the height using the model. Determine the height of boys after 48 months or at 48 months of age, and also compare to the actual. They're giving us the actual. So let's write it down. Problem 127 on page 296. So this is an application of exactly what we are discussing right now. 127, On 296, yes. So here it is. So we are given the function, which is f of x, 2.9 the square root of x plus 20.1. We decomposed it and we said in part A, it's the square root of x, vertically stretched by 2.9 and shifted up 20.1. Part B, they're asking us to find what happens at when x equals 48 months. And then compare to actual. And they're giving us the actual. The actual, they say it's 40.8 inches. The other thing that I have to mention is that x is in months and f of x in inches. So f of x is the median height. Median height. Okay.
Let's say 40.8 inches.
That's what they gave us. Yes. 40.8, yes. Okay. So let's go to y equals and punch in 2.9 times the square root of x. You know I love parentheses, so you don't have to. Maybe your calculators are sophisticated enough, they don't need parentheses. But I have to put parentheses, just a habit. Okay, so after we put it in,
So is this a free program you can get?
not really sure. We have a certain number of licenses here, and only by request they install it on the Podium computer. So I'm not sure, and maybe now we may be free.
Find a deal for the students, yes.
You cannot use your laptop during the test anyway, so it's up to you. Okay, so second and table, we're going to plug in 48. And we get 40.192. So f of 48, I didn't ask you, but obviously I'm sure I should have asked, my apologies. How do we determine the height at 48? You have to plug it in, correct? Okay, so this is 2.9 times the square root of 48 and plus 20.1. The calculator gives us 40.192 inches. Now they're asking us a question here in part B. Do you consider this a good model? So the actual experimental value came up with 40.8 at 48 months. The model that they came up with gave us 40.192. Are you happy with the answer? Do you think that the model is good enough? At least for 48 months. I don't know, maybe at 39 months is not that good. I don't know. But at 48, what do you think? I think it's pretty good. I think it's pretty good. It's not a life-threatening situation, right? We have to look at the tiny. I think 40.8 and 40.19 or almost 40.2 are quite close. I would say it's a good model. Now, in part C and part D, they're asking us to do something that we had on this previous test that I just returned today. Use the model to find the average rate of change. And some of you determined the values but did not determine the rate of change. You just plugged in numbers in the function, you got them correctly, but you didn't finalize the average rate of change. So here's another problem, so we can connect it to the previous test. So find the average rate of change in inches per month between birth and 10 months. So this is the average rate between 0 and 10 months. And in the last question, they're asking us the average rate between 50 and 60 months. Between 50 and 60. Remember, the average rate of change is a ratio. And of course, the top will be f of 10 minus f of 0 over 10 minus 0. And can anyone dictate the second one?
F of 60 minus F of 50 over 60 minus 50.
That's it, the slope of the line going through those points. Excellent. Bless you. So now let's plug in all these numbers. So we need 0, we need 10, we need 50, and we need 60. I'm going to copy them. So then the first one has 29.27 minus 20.1 over 10. And the other one has 42.56 minus 40.606 divided by 10. Any questions on how we got those numbers, or is there anything that you would like to ask before we calculate? We're not finished. Any questions, please? Any questions? Okay, so let's determine the first one and let's determine the second one. So 29 minus 20 is about 9.1 divided by 10.91 measurement unit. Without the measurement unit, the measurement unit is a composite measurement unit. Measurement unit for the top over the measurement unit for the denominator. What is the measurement unit for the top? What do we measure f of x in? Good. What do we measure x in? Good. So then the answer is? So here's what it means. It means that according to the study, between the 0 months of age and 10 months of age, the height of boys changes at, or with, or by almost per, that's it, almost 1 inch per month. Okay, good. So now 42 minus 40. Okay, divided by 10, so roughly 0.2. And the measurement unit, please. Of course. Does it make sense? So between the ages of 0 and 10 months, they grow fast at almost 1 inch per month. But between 50 and 60 months of age, their growth slows down. It's considerably lower, by 5 times lower almost. 0.2 times 5 is 1. Is this clear from the graph? It's very clear from the graph. So here's why. Because the slope between 0 and 10 is this, and the slope between 50 and 60 is this. Which one is steeper? This one or this one? Right. So they grow so much faster between 0 and 10 months than between 50 and 60. Good. So that was a specific example based on transformations. Okay. We have one more to look at. The ones that we looked at so far are pretty self-explanatory, I would say. I wouldn't expect you know us to understand them right away, but I think we had plenty of examples. So we had this one was a vertical, stretching and shrinking. Done. The very last one is horizontal. This one is a little bit more difficult to understand. That's why I normally leave it at the end. It's not that self-explanatory. And to be exact and be honest with you, it's kind of the opposite what you would expect of what you would expect. So let's slowly look at the following situation. My markers grew legs. Okay. So let's suppose we are looking at x cubed. And for some reason, I would like you to determine f of 2x and also f of 1/2 x. We know how to evaluate functions, although I saw a few mistakes on the test in evaluating, but we know how to evaluate this. So, can anyone tell us how to determine this? The function is x cubed, and we want to change x into twice x. And then later on into 1/2 x. So can you please tell me what to write? Excellent. Like this, correct? You meant cubed, but you meant like this, in parentheses, I hope. Okay, perfect. So then let's simplify this. We know how to raise a product to a power, so what do we get? Excellent, thank you very much. Good, so now forget all this for a moment. Forget where this is coming from and let's just talk about it. X cubed. This is x cubed, correct? And we discussed 3 minutes ago what happens when there is an 8 or a 2. We look at 2 or 8 outside. What happens? How? Exactly. How? Vertically, correct? So x cubed becomes 8x cubed because it's a vertical stretching, correct? But look at what happens horizontally. Look at my hands. I know I look silly, but it's okay. So this is x cubed. No, it's not stretching. Look again. What happens on the, no, it doesn't. I'm talking about the x, on the x-axis. I'm talking about horizontally. Wait. So look at what I do and tell me what happens horizontally, not vertically. I'm asking about horizontally. So here's x cubed, and this is 8x cubed. What happens horizontally to this graph, not vertically? Exactly. So it's the opposite of what you would expect. Yes. So changing x into twice x is a horizontal shrinking of the graph. Say it again. I couldn't hear you. Your bag is in the way.
No, I lost my voice over the weekend.
Okay.
No, I'm just thinking out loud. How to
Okay.
expect people to remember.
This is the only one that is opposite. Everything else is common sense, but this is the only one that is opposite. But that's why I show you looking silly, because I'm hoping that will help you. Okay, now let's look at 1/2 x. F of 1/2 x.
So the parentheses 1/2 x, close parentheses cube.
Excellent. And the answer simplified without parentheses will be? One over 2 times 1 over 2 times 1 over 2 cannot be 3 over 8, but it will be 1 over 8 x cubed. Good. So here's what happens next. Forget about where it's coming from. This is x cubed. What do I do to x cubed if there is a 1/8 in front of it? I cannot vertically stretch it.
Is this when you count?
Good. What happens horizontally then?
Straight.
It's the opposite of what you expect, right? So when we change x into 1/2 x, it does not shrink, but it stretches horizontally. So this is a horizontal stretch. Okay, let's look at an example. Because it's a very good question, how do we remember this? Here it is. Let me see.